Oh, okay, welcome to the third algebra session of Mind and Zed. Let me share my screen. Okay, so today we will be going over functional equations, and we will be covering an intro to functions and functional equations, some substitutions, injectivity, and finally surjectivity. So what are functions? Functions are basically a rule that defines a relationship between an input and an output. So you could think of it as a machine where you put in a number and then it will give out a number. So the set of all possible inputs is called the domain of a function, and the set of all possible outputs is called the codomain or the range of a function. A function is usually denoted by f of x, but it can also be g of x, h of x, a of x, etc. So now I'll ask you guys, which one is a function? F of x equals 1, or f of a equals 1, 2, 3, 4, and dot 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 100 for some a. Which one would be a function? Well, there's a rule about functions where each input can only have at most one output. So if you look at the second one, it has 100 outputs for a value of a, so it must not be a function. So the only one that can be a function is f of x equals 1, because every single x, or just some x, equals 1. So this is basically a reiteration of the previous slide. The first one is the first drawing is a function, and the second one is not a function. Do you guys know why? It's because the one of the second thing maps to -0 and 15. But this means an element maps to two other elements, which means it can't be a function. Okay, so now what are functional equations? Functional equations are a branch of Olympiad algebra that basically creates a relationship between a function or multiple functions. So these problems appear very frequently, such as the NZMO and the British Math Olympia, and require knowledge of many techniques, and you need to be very creative. So an example of a functional equation is this one. F of x plus f of y equals 2x plus 2f of y plus 1. And this is from NZMO 1 of 2020 Q5. So typically, a functional equation abides by a certain layout that starts with find all f of x, or either ends with find all f of x or starts with it. And then it asks you to find all functions. So if you miss one function, you will lose a lot of marks. So we're always trying to find more solutions. And then it's usually f, and then there's this symbol, x, arrow x, which basically tells us f maps from domain x to range x. I'll call this one x1 and x2. So this is specified in every single functional equation problem, and usually it's real numbers. Does anyone remember the symbol for the domain of real numbers? Can someone tell me in chat? Yeah, Josie, you're correct. It's a letter R. So it's basically a capital R. And then it can also be the natural numbers. Does anyone remember the symbol for the natural numbers? Can someone tell me in chat? Yeah, it's a letter as well. There's a big hint in the word natural. Okay, the letter for the domain of natural numbers is n. And then rational numbers. Does anyone remember the domain for rational numbers? So rational numbers are also known as quotients. And what's the first letter of the word quotient? It's a Q, right? So the real numbers, the natural numbers, the integers, and the quotients are usually used for functional equations. And then finally, the problem will present an expression involving f of x. So this is basically the heart of the problem, and you have to manipulate this expression to find f of x. So this is basically a small diagram that shows us the number domains. It's natural, integer, rational, real algebraic, and real. So there's basically four main strategies in functional equations, and most functional equations uses at least two or three of them. So it's substitution by plugging in values, injectivity, surjectivity, and bijectivity. Does anyone know what substitution is? It's where you set x to be a certain value, right? Like 1, 0, -1. So this is a basic functional equation. For all f that maps from R to R, find f of x such that x times f of x equals x. I'll give you guys 30 seconds to try that. So what should we do to get f of x equals something by itself? What's your first response? Can someone tell me in chat? Okay, so basically, if you see x and x on both sides, your first response would be to divide by x, right? You would have f of x equals 1. But is this actually true? Is this actually true for all values of x? It's not necessarily true for all values of x, right? Because if you subtract by x on both sides, you would have x times f of x minus 1 equals 0, right? But we run into a problem when we have x equals 0, because if x equals 0, the equality already holds. So we have to say f of x, f of 0 can be anything, or we can either say is not defined. So now we'll move on to the first method, the substitution method. The main purpose of the method is to cancel out terms and to simplify the algebraic expression. So when you have like an algebraic expression such as x squared plus x plus 3, how would you substitute x for a? It will turn into a squared plus a plus 3, right? Similarly, for functional equations, if you have f of x equals x plus 3, if we plug in x equals 2, we have f of 2 equals 2 plus 3 equals 5. So I'll give you guys a small challenge is to solve the problem that's on the slideshow. So it says a times f of x plus f of 1 over x equals ax, where the domain of f is the set of all real non-zero real numbers. So try to solve this for f. Okay, I'll give you guys a hint to do this. What would your first response be to try cancel something out? Can someone tell me in chat? Okay, Josie says to divide by a, but then you would have 1 over a times f of 1 over x equals ax. Oh, equals x. So dividing over a doesn't work. So the only other way to do it is by substituting for x, right? Because that's the only other thing that we can change. So if we substitute for x, what value should we substitute for x? 1? Okay, let's just try some small values. If we have x equals 1, then we have a f of 1 plus f of 1 equals a, right? Is this helpful? It's not really helpful, right? So how would we cancel out the x or the 1 over x? Which part looks the most annoying to us right now? It's a 1 over x, right? So one substitution that's not just plugging in 0, 1, or -1 is plugging in things related to x, such as x equals 1 over x. Or we can write p x turns to p 1 over x, which is the proper notation. So if we plug in 1 over x into this expression, what would happen? We get a times f of 1 over x plus f of x equals a over x, right? And then we have a times f of 1 over x, and we have f of 1 over x. So how would we cancel that out? Simultaneous equations, right? So how would we use simultaneous equations to cancel that out? We multiply the first expression by a, right? So we have a squared f of x plus a f of 1 over x equals a squared of x, right? So now we can cancel out a f of 1 over x, which gives us something times f of x equals something related to x. So if we use simultaneous equations, we have a squared using second expression minus first expression, we have a squared f of x plus, minus f of x equals a squared times x minus a over x, right? But then what is the constant being multiplied to f of x on the left-hand side? It's a squared minus 1, right? Times f of x equals a squared x minus a over x. So what is f of x? We just divide by a squared minus 1, right? Which gives us f of x equals this expression all over a squared minus 1. So this problem originally looked quite complex and hard to solve, right? But by using substitution to cancel out terms, we've made it into quite an easy thing to solve because it's just a constant multiplied to f of x. So substituting is very good for simplifying problems and making problem statements look more helpful. So this is some shorthand notation I used on the previous slide, where I wrote p of 1 over x, which is basically plug in 1 over x for x. By plugging in x equals 1 and y equals 2 into the equation, f of x plus y equals f of x plus f of y. We find that something. But instead of writing all of this, we write using p of 1, 2, we get ... So here are some exercises, and the range and domain are both the real numbers. I'll give you guys 30 seconds to do the first one. Oh wait, sorry, I have to make this one positive real numbers. Okay, so how would we find f of x by itself on one side? We just divide by x, right? So this one's quite trivial. You just divide by x to get f of x equals a over x. And because it's positive reals, it's defined for every single number x. And then I'll give you guys some time to try the next one. Okay, so does anyone have any ideas about how to do the second one? We want f of x to be equal to something, right? So how do we go from 2x to x? So basically we just plug in x over 2 which gets us f of x equals x over 2 squared. Right. And what is x over 2 squared? It's equal to x squared over 4. And then for the final one, we can keep it at real numbers to real numbers. Oh, I'll give you guys 30 seconds to do this one as well. So basically, we want to transform this thing into x, right? So what would be the first step? We want to get rid of the constant, right? So we change it into x minus 1. And then how do we get rid of this thing? 3 is being multiplied to x. So how would we get rid of the 3? We divide it, right? So it should be x minus 1 over 3. So we plug in this value. And then the thing is already solved, which gives us f of x minus 1 over 3. Does everyone understand? Okay, I'll take the silence as a yes. So in this question, we just want to look at what's the most annoying to deal with. So what would be the most annoying to deal with? Can someone tell me in chat? Because what is the end goal? The end goal is to find f of x, right? So in finding f of x, what would be the most annoying in this expression? It would be x plus 3, right? Because it's telling us the value of f of x plus 3, but it's not telling us the value of f of x. So how do we get rid of this? We just plug in what number or what value? Can someone tell me in chat? To get rid of the plus 3, we just need to do a minus 3, right? So we just plug in x minus 3, and then we have f of x minus 3 plus 3 equals x minus 3 squared plus 8 times x minus 3 plus 16. And we are done. So now I'll give you guys a chance to do this one. Final functions f that maps from the reals to the reals such that f of x plus x times f of 1 minus x equals x. I'll give you guys 2 minutes to try this one. So this problem has something to do with a substitution, right? So what should we substitute x for? Can anyone tell me what they think we should substitute x for? Okay, so Eliza just asked, how can we make a substitution to make both equal to x? So making x and 1 minus x equal will be quite hard, and it will only work for certain values of x. So that's probably not the right substitution to do. Instead, we should make the same substitution as this problem, right? Something that lets us cancel one of the terms using simultaneous equations. So what should we substitute x for? Good job. We should substitute for 1 minus x. So when we substitute for 1 minus x, we have f of 1 minus x plus 1 minus x times f of 1 minus 1 minus x equals 1 minus x. But what is 1 minus 1 minus x? Can someone tell me in chat? It's just x. So now we can either cancel out f of x or we can cancel out f of 1 minus x. Which one would give us what we want in the problem? We want to cancel out 1 minus x, right? F of 1 minus x. So what's being multiplied to f of 1 minus x in the problem statement? It's being multiplied to x, right? So we should multiply our equivalent expression by x. So now we can use simultaneous equations to cancel out x times f of 1 minus x, and we would have x minus x squared minus 1 because of the f of x in the original times f of x equals the right-hand side minus the old right-hand side, x times negative x, right? So how would we find f of x? Can someone tell me in chat? Okay, so basically you can divide by this expression, and then would you be done after dividing? So would you be done after dividing by that expression? You wouldn't, right? Because there might be values of x such that f of x is not defined. And then you would have to do some casework to find those values. But that takes a bit too long, so I'm just going to move on to the next problem. So solve the functional equation where a squared is not equal to b squared, and a times f of x minus 1 plus b times 1 minus x equals cx. I'll give you guys 2 minutes to do this one as well. Can anyone tell me in chat about the substitutions that they have thought of? You have to make two substitutions to do this problem. Okay, I'll just tell you guys one of the substitutions. So basically we have x minus 1 and 1 minus x, right? If you have experience doing functional equations, you could just transform x into x minus 1, right? Because it's across the reals. And then you would have a times f of x plus b times f of negative x equals c times x plus 1. But then another thing you could just do, if you don't have much experience in functional equations, you could just plug in x plus 1, and you could also plug in 1 minus x. So what would this give us? It gives us, first, by plugging in x plus 1, we have a times f of x plus b times f of negative x equals c times x plus 1, right? And then by plugging in 1 minus x, we have a times f of negative x plus b times f of positive x. Oh, wait, no, equals c times 1 minus x. Okay, so I can't say positive x because x may be negative as well. So what should we do to cancel out one of the terms? Should we cancel out the one with negative x or the one with positive x? Oh, wait, no. The one with minus x or the one with just x? It doesn't really matter. But then I'll just do the one with minus x for the sake of simplicity. So what should we multiply the first equation by? We could multiply it by a, we could multiply it by a over b. It doesn't really matter, but I'll just multiply it by a, and I'll multiply the second equation by b. This gives us a squared f of x plus ab f of negative x equals ac x plus 1. And the second one gives us ab f of negative x plus b squared f of x equals bc 1 minus x. So now if we cancel these out by this equation minus this equation, we have a squared minus b squared times f of x equals ac x plus 1 minus bc 1 minus x. Right. And then I'll leave the rest to you guys. You can do it in your spare time. So we can skip this one. You guys can also do this one in your spare time. And then we'll move on to injectivity. So for a function f that maps from domain A to range B, f of x is injective if f of A equals f of B implies that A equals B. So firstly, what does this statement mean? Can someone tell me in chat what they think this statement means? How is this statement important? And how could it be used in a functional equation? Oh, okay. So basically, if we have f of something 1 equals f of something 2, then we could just use something 1 equals something 2. So basically, we're dividing by f. So what does this also tell us? This also tells us that for all a in domain A, for all lowercase a in domain uppercase A, we have that f of A maps to a unique element in range B. So what does this look like? It looks like this diagram. So in the first diagram, we have that f is not injective because we have these two dots mapped to a single element in B. But then in the second diagram, we have that all of the elements or the dots in A mapped to a unique element in B. Does everyone understand? Okay, so using a similar diagram shows that if f and g, so f and g are both functions, are also both injective functions, then we have f mapping from A to B, g mapping from B to C, then if then g of f of x is also injective. So basically, this exercise is showing that if you have these dots mapped to a unique thing in these dots, and these dots in group B mapped to a unique thing in an imaginary group C that's not in the diagram, then show that if you have G of f of x, so it's basically all the outputs from f as inputs into G, then we have that all of those are mapped to a unique element in C. I'll give you guys 30 seconds to try this out. So essentially, from the problem statement, we have, so this is f, and this is g, right? So what is g of f? G of f, wait, g of f would be this thing. So f tells us all the elements in A are mapped to a unique element in B. So we say, such as this one. Oh, wait. Okay, doesn't matter. This one. And then all the G tells us that all the elements in B are mapped to a unique element in C, which tells us this one. Doesn't matter which ones you're mapping to, as long as they are unique, then that's fine. So obviously this tells us that g of f of x is injective. Because if you look at it, it's like this, and this. Does everyone understand? Can you tell me in chat? So similarly, show that if g of f of x is injective, then we have f of x is also injective. Can you guys tell me in chat? I'll give you guys 10 seconds to think about this. So what is another way to think of injectivity? It basically tells us that if A is not equal to B, then f of A is not equal to f of B, right? This is the contrapositive of the first statement. Wait, where is it? Of this one. Because this one implies that A equals f of A equals B implies that A equals B. Basically uniqueness. So if f of x is not injective, then there must be A and B such that f of A equals f of B, right? Is everyone following? And if we have that A is not equal to B and f of A equals f of B, then obviously g of f of A is going to equal g of f of B, right? Because we could call this one, we could say f of A equals capital X, f of B equals capital X, then obviously g of x equals to g of x, right? So basically this tells us that if g of f of x is injective, then f of x must also be injective, because we can't have two values being equal to each other when plugged into g of f of x. So we'll have an example problem on injectivity. Find all functions f that maps from the integers to the integers, such that x plus f of y equals f of x plus y. So this one introduces a new substitution that you guys haven't seen before, but then that's only used in the later stages of the problem. So I'll give you guys 2 minutes to try out, find some ideas about this problem. You guys don't have to solve it, but just try to find some insight. So what are some easy substitutions that we can do? Going back to our substitution slides, some easy numbers to plug in are 0, 1, and -1. And why do we use substitutions? It's always to cancel out some expression. So what expression can we remove? Which ones look quite easy to remove or quite detached from the problem equation? Can someone tell me in chat? Y, right? So if we set y equals 0, we have that f of x plus f of y equals 0 plus f of 0 equals f of x, right? But what's something else that we can plug in as 0 that might be linked to injectivity? Does anyone have any idea? Don't be afraid. It's just another like basic substitution. Okay, so the other substitution we make is x equals 0, which tells us because x is within f of x plus f of y, right? Which is kind of annoying. If we have f of y equals to f of 0 plus 1. So what does this tell us now? What is special about f of 0? So we know that each element in the domain of f maps to at most one element in the range of b, right? In the range b, because it's the definition of a function, which tells us that f of a constant must also be some unknown constant at this stage, right? So we know that f of y equals to y, and if we have f of a equals to f of b, where a, b are not equal, what does this tell us? This tells us that f of a equals f of 0 plus a equals f of b equals f of 0 plus b. But what's the issue with this? Because we said that a, b are not equal, right? So f of 0 plus a can't equal f of 0 plus b. So what does this tell us now? What did we just prove? We just proved that f is injective. So because f is injective, we know that x plus f of 0 equals x. What does this also tell us? F of 0 equals to 0. So what's so important about f of 0 equaling 0? It's because of this, right? F of y equals f of 0 plus y. Because f of 0 is 0, we can just remove this, and we know that f of y is just equal to y. So what does this tell us now? This statement allows us to make a new substitution in this problem. So we know that we can substitute, oh, can substitute for constants, can substitute for expressions involving x, but we can also substitute for f of something. So this is quite important in solving this problem. How would we substitute for f of something, knowing that f of y equals to 1? Can someone tell me in chat? Does anyone have any idea? Basically, this tells us that if we make this substitution, y equals x, equals f of x, then we will have f of x plus, what's f of x? Oh, never mind, y equals f of t. We would have f of x plus t equals f of x plus f of t. What would happen if we also plug in y equals f of x? We get f of 2x equals 2f of x, which is not as helpful as the one below. So what does this tell us? By the way, this is a famous functional equation called Cauchy's functional equation. And although this looks like it's very hard to approach, f is across the integers, right? So basically, we could just, what's the increment between integers? The increment between integers is always 1, right? Plus or minus 1. And we haven't specified t to be anything yet. We just said y equals f of t. So if we have t equals 1, with f of x plus 1 equals f of x plus f of 1. So what algebra technique or problem-solving technique can we use on this expression? We can use something known as telescoping, or we could use something known as induction. So basically, we know that f of 1 equals f of 1, right? That's obvious. And then we have f of 2 equals 2 times f of 1, because it's just f of 1 plus f of 1. F of 3 equals 3 times f of 1. And dot, 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 we have f of n for any integer, positive integer, equals n times f of 1. What about the negatives? So we have f of negative 1 equals f of negative 1. And then dot, 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 f of negative n equals negative n times equals n times f of -1. But if you look closely, these two are still not connected yet, which means we haven't finished solving the problem. But if we have f of n plus 1, how do we relate it to f of n? Well, if we have f of n, how do we relate it to f of n plus 1? Sorry. It's f of n plus 1 plus f of -1, right? Because n plus 1 minus 1 is just n. So now oh wait, but what is f of n plus 1? We know that f of n plus 1 is the same thing as n plus 1 times f of x. Oh, sorry, f of 1. And what is f of n? F of n is also very simple, right? This is for positive n. F of n is just n times f of 1. But we have n times f of 1 equals n plus 1 times f of 1 plus f of -1. So what is f of -1? F of -1 is just simply equal to negative f of 1. So now we've related this sequence and this sequence by telescoping. How do we complete the problem? Because we know that everything, f of n, is in the form of n times f of 1. But the problem is still not solved, right? Why is it not solved? Can someone tell me in chat? The problem is still not solved because we don't know what f of 1 is, right? F of 1 is still not confirmed. So if we plug in f of 1 back into the original equation, we will be finished. So I'll give you guys 2 minutes to plug in f of 1 into this equation, and then you guys can tell me the answer to what f of x can be. Or if you can't figure out what f of x can be, tell me what f of x can't be. So basically, we have f of x plus y times f of 1 equals x times f of 1 plus y. Right. But then we know what f of n is, and this thing is just one of those n, right? So we know that x plus y f of 1 times f of 1 is equal to x f of 1 plus y. Has anyone figured out what f of 1 is? So basically, we can just cancel x times f of 1. And now we know that y times f of 1 equals to y. So what is f of 1? F of 1 is just simply 1, right? So now we know that f of x equals x. Does everyone understand? This problem is quite complex. Okay, we'll move on to the next topic, surjectivity. It's basically where all of B is mapped to by some elements of A. So if you think of B as a canvas, it tells us that B is fully covered by the paint, which is A. And how is this useful to us in Olympiad problem solving? Can anyone think of any creative uses for this? I think I wrote it in the slide. We can set f of A to be some expression that we want. So this is also very useful in canceling terms and getting expressions that we want. So what does surjectivity actually mean? If f is surjective, wait, then every single element in B has a corresponding variable by f in A. But can I have more than one corresponding variable, or is it only one corresponding variable? Can be more than one corresponding variable. But then if it's only one corresponding variable, then it's called bijectivity, but we don't have enough time to cover that. So the first diagram is surjective. We have A, B, C, D mapping to each one of the elements in B. So every single element is mapped to. And the second diagram is not surjective. We have A, B, C, D, but it doesn't cover all the elements of B because G has nothing that maps to it by F. So using a similar diagram to this one, show that if F and G are both surjective, then we have that G of F of X is also surjective. I'll give you guys 2 minutes to do this one. So basically, if we use a similar diagram, we have A, we have B, and we have C. So we can color in B because we know that all the things in B will be mapped to. And then, because F is surjective, right? And then by G being surjective as well, we can similarly color in C, because we know it will be surjective. And remember, G of F of X basically inputs all of the outputs from F into G. So if we have something going from A to B, and G of F of X puts it from B, from that element in B, to some element in C. So we'll basically just get a combined path. So this tells us that if F and G are both surjective, then G of F of X will also be surjective. And then show that if G of F of X is surjective, then F of X is also surjective. I'll give you guys 30 seconds to do this one. So essentially, if G of F of X is surjective, then we can use this diagram to know that these extended paths basically cover all of C, right? But then how would we prove this? We would prove it by assuming that G of F of X is not surjective. If G of F of X is not surjective, then there's some element, is some A within domain A that, within the range C, such that G of F of X does not have any X that maps to it. Is there any issue with this? Oh, yeah, sorry, wrong one. G is surjective. Oh, it doesn't matter. Okay. Basically, this tells us that there's something. Oh, wait, no, it doesn't matter. So we need G to be surjective. If G of F of X is surjective, then that tells us that if G of X is surjective and G of F of X is not surjective, what happens? That means f of x is not surjective. Right? But if g of x is not surjective and g of f of x is surjective, then what does this tell us? I need to make another fix to this. Mostly surjective. If g of x is not surjective and g of f of x is surjective, what happens? This tells us that the number of elements in C is compromised. It must be smaller, as in it must be smaller than the number of elements in A. Because we could view this as basically like a road, but then the road has many cracks in it. And if there is a crack, then cars can't drive past that part of the road, right? But then since it's not surjective, then there must be a few cracks, at least one crack in the road, right? So the cars can't drive past that part of the road, which tells us that that part is compromised for those elements that map to the same thing. So here are some exercises for surjectivity, which is kind of confusing. Is f of x equals x surjective? Can someone tell me in chat? So basically, for any value of x within the reals, we just need to plug in that same number to get it, right? Which tells us f of x maps to all the reals. But is f of x equals 0 surjective? Of course it's not, right? It only maps to 0. And is f of x equals x squared surjective? It can't be, right? Because x squared only, it must always be positive or equal to 0. So it basically only covers around half of the numbers within the real numbers because it can only map to positive real numbers or 0. So now we won't be doing the last two questions because these take a long time to explain. So does anyone have any questions about what we covered today? You can type them into chat. Okay, how's everyone doing for NZ-1? How many problems has everyone done? 2? Nice. Yeah, it is hard. Anyone else? 3? pretty good. Oh, okay. Okay. So your next session will be, is it geometry? The next session will be geometry, which is on the 29th of June, which is next week, Saturday, from 6:30 to 8 p.m. And it will be with Ethan and William. Okay, thank you guys for coming. We can end the meeting now. You guys are free to leave. But if you have any questions, you can ask them. You can stay back and ask.